In this clip, we're going to look at how wireless channels changes with time, or we're going to look at the rate of change of wireless channels. And this mainly caused by what we call Doppler effect. Okay, so let's see uh, what's going on here. We have a base stations which receive signal from a mobile which is in some moving car, right? So the car could be coming toward the base stations, right, with relative velocity v, or it can go out away from the base stations with speed v. And let's assume that the carrier frequency is equal to fc hertz. Okay, and this gonna cause a dropper, right? There's gonna be a change in carrier frequencies, even though the change will be not many hertz, but it's gonna cause the change in time domain in wireless channels. Okay, now we can compute and calculate the maximum dropper shift that occur with this scenario. Maximum Doppler shift is equal to Fc, which is carrier frequency, multiplied with the v, that's relative velocity. So here only the mobile is moving and the base station stay put. Relative velocity is v. You have to convert this in terms of meter per second, divided by c. This is the speed of light, which is 3 multiplied with 10 to the power of 8 meter per second. And this will affect the change of the channel in time domain. To really study how the channel is changing, right, we're gonna do some analysis and simulations later. So we'll have certain assumptions. Here, the system that we are considering is having transmission bandwidth very small, right? So small transmission bandwidth. So small here is in terms of kilohertz. Example of narrowband transmission is 1G system, where the channel is only 30 kilohertz wide, and in 2G it's relatively narrow too. The bandwidth is 200 kilohertz. Okay, and even 4G and 5G, which employ OFDM, and if you only look at sub channels in OFDM, only one sub channels, but of course in 4G and 5G they have 1000, right, sub channels. But if you look at each sub channel, the bandwidth is narrow too. It's about 20 kilohertz. Okay. Now, why this is a factor? Because if you have a small bandwidth, then if you look at sampling period, right? So we are talking about discrete time system. The sampling period is 1 over W seconds. So the system sample the signal every 1 over W seconds, right? So if W is small, 1 over W is large. That means our system has very low resolutions. Okay, so what is the effect of that, right? So if we look at wireless channel, right? So we have a transmitter, we have a receiver, and let's assume that there are a lot of objects which gonna scatter the signal, right, between transmitter and the receiver. Okay, and there's no line of sight path, so there's no direct path from the transmitter to the receiver. Okay, so if we are sending the test signal, right, through the transmitter, so the test signal here is impulse at time 0. You see that the signal will go to many different paths, because there's a lot of objects in the paths, and it could, you know, reflect the signal or reflect or scatter the signal, and at the end the received signal is composed of signals from multiple paths. Okay. Now, if you look at channel impulse response, right? So at the output of the receiver, after we sending the impulse, we'll receive channel impulse response. And you see that h of t represents channel impulse response. Okay. So there's gonna be a few pulses now instead of one because of many different paths. So here we have 1, 2, 3, 4, 5, 6, 7. So 7 different paths that is coming to the receiver. And you see that delay spread is very small. So this different paths are sticking together, right? So the delay are very similar. And since our system has low resolutions because of the low bandwidth, when the system sort of see these different paths, they cannot distinguish them. So in discrete time system, right? So here before in analog uh, uh, model, the T is time, it's continuous time, right? And now is if we are talking about discrete time system, then the N is the time index, right? So after we do sampling, right, this different paths might got lumped together into uh, only one filter tab or one path basically. And this is the the channel gain of this one single path is composed of all the gains of different paths, right? So it's the sum of different paths. And if we have many paths, right, the sum of different random variables, right, we can sort of model them as Gaussian random variable. So H, which is the magnitude, which is the channel gains, the channel coefficients of this system, we can model it as Gaussian random variable. It's complex Gaussian random variable. And if we consider only the magnitude, right, which we're gonna term it as variable R, this gonna behave like Rayleigh random variable. Okay. Okay. So with this system in mind, with these assumptions in mind, uh, we can model our channel by just one single variable, right? So the channel gain is only one number, but actually we can looking at it in two different components, right? So the first component that we are not really talk about is the last scale fading, right? So this is LP is the last scale fading, right? And we look at this at the beginning of the course, right? So LP change very slowly, right, over a large distance, right? So for now, we are not considering this, right? Okay. So we are only concentrate on the change of this term, right, which is this small scale fading, right? So we're gonna look at the magnitude square of the channel gains. Okay, so we're gonna look at the behavior of this mainly because this is gonna change faster than this. So we're gonna assume that LP stay relatively constant, while this small scale factors will change with time, right, at much faster rate. Okay. Now, if we sort of do a simulations, right, only looking at the magnitude of this channel gains, uh, uh, we are looking at in time domain, right? So we might see something like this. So the channel changing, right? Sometimes it's good, sometimes it's bad, so it's coming down, something like this. And we could find the average, right? The average over time, right? So let's assume this is the average, the dash, the red dash line, right? So this is when we do average, we can looking at root mean square average, right? So RMS is root mean square average, right? So how do we find root mean square average? You take the magnitude of the channel gain raise it to power 2, right? And then you sum it up, right? So or you integrate over the variable t, which is the time, right? You integrate over this period, right, from 0 to big case t, and then divided by the time. 1 over t, and then take the square root. Okay, and now what you do is you expand the time, right? You take uh, the t, right, the period t to be really large or go to infinity. Okay, and then this is gonna give you the root mean square value, right? So basically it's the average. Okay, so once we get the average, so let's see how the magnitude of the channel gain deviate from the average. So we can looking at this term, right? So the R divided by the average and raised to 2 power 2, right? And we're gonna convert this into dB, right? So we're gonna look at the ratio of these two numbers and then do it in looking at it in log scale. So 0 here is 0 dB, right? That means it's the average, right? So which is the red dash line, right? Now maybe we wonder, right? How many times or how often the channel dip below the average. For example, uh, what if it's getting so bad that the channel is minus 10 dB below the average, right? So minus 10 dB could be the threshold, right, that we are concerning. Okay, so for this particular example, so here's minus 10 dB, and you see that right here, right, the channel dip below minus 10 dB, and right here, right, so twice. Okay, so the first time, right, it dipped below minus 10 dB, and this is how long it's going to be in that bad state, right? Okay, whatever this tau 1 is, so how many milliseconds or microseconds there, right? And the second time is right here, right? So the time period might be tau 2, and in the simulation that you're gonna do next, right, we're gonna simulate the change in the channel, right, using Clark's model, right? And then we're gonna see, right, if we have different threshold, we want to see how often the channel dip below that threshold. In this example, it dips below the threshold twice. Okay, besides the number of times, we want to look at, okay, each time that it dips below a certain threshold, how long it stay in below the threshold, right? For this one, right, so the first time is tau 1, the second time is tau 2, and maybe we want to find the average of the time period that's the channel it's gone below certain threshold. And that's what you're gonna do next.